Saudi Arabia. He earned his PhD in Mechanical and Aerospace Engineering from International Islamic University, Malaysia in the year 2020. Sir has done Master of Science in Aerospace Engineering at Jawaharlal Nehru Technological University, Hyderabad in the year 2014. Sir has done Bachelor of Science in Aeronautical Engineering from Visvesvaraya Technological University in the year 2010. Dr. Aabid has gained valuable teaching experience in different institutions across the globe. Dr. Aabid has been recognized among the world's top 2% scientists by Stanford University. Sir is having around 3,000 plus citations as indicated in the Google Scholar. His research interest spans on a broad spectrum, including solid mechanics and structures, fluid mechanics and control, as well as material science. His achievements have been recognized with various awards throughout his career, including Outstanding Student Award, Outstanding Researcher Award, Best Paper Presentation Award. Beyond his academic and research commitments, Dr. Aabid is also actively involved in professional societies around the world. I would like to now welcome Professor Hamid Bula to take over the session. Welcome, sir.
Good evening to everyone. Thank you so much to Dr. Janardhan for giving me such a good introduction about me. And I'm really thankful to the JMRIT calling me as a presenter for this faculty development program. And also, I would like to thank everyone, principal and the organizing committee that calling for me for this presentation. Let's start my presentation. Can I share my screen now? Is allowable?
Yes, sir. You can share your screen.
Yeah. Okay. Fine. Share. Okay. Yes, you can see my screen.
Yes,
Hello?
sir. I can see your screen, sir. Yes, sir.
Yes, fine. Thank you so much.
Yes,
I'll start my presentation. As I know, since last 2-3 days, there's a presentation going on the additive manufacturing with the different from the different organizations and expertise on this field, and I will add my points here as well about the automation in additive manufacturing. As Dr. Janardhan introduced about myself, I'm Dr. Abdul Aabid, currently working as a researcher at Prince Sultan University, and I also am recognized world's top 2% scientist by the Stanford and the elsewhere. Basically, my research fields, I'm working on smart materials, material science, and fractures and integrity of any object. And somehow I also did the research on additive manufacturing. Recently, one student, he graduated masters from International Islamic University, Malaysia, under my supervision, and he did very good research. Also, we published a very nice paper in additive manufacturing. So based on that knowledge, maybe I can able to deliver some points with you all about what's the current updates on additive manufacturing and automation techniques and recent technologies added in that additive manufacturing. So let's start my presentation. In today's presentations, what I'm going to talk about the first introduction. As you can say, the introduction is very common for additive manufacturing, what I am giving today. And also, since you have this is the third day of your faculty development program, also I believe that you have learned many things about the additive manufacturing since today, and hopefully by next 2 days also you will get more knowledge about this additive manufacturing. Next, I will talk about the integration of automation with AM, which is the aim of my current presentation. So, like let's say if I'm very particular on this point, integration of automation in with the AM, what happening and how it is working, and what are the outcomes based on these automation systems. So next, I will move about the technology infrastructure because since we are in 2025 and we have a lot of technologies and that we can implement in different field, especially in additive manufacturing as well. So I will give some overview about the technology infrastructure. So after that, I will move to the strategic value and impacts. Yes, definitely, because this is one of the main important point that I can say it. Once we are doing this, we are in the recent technologies adapting for the additive manufacturing. So what the impact is happening in the current scenarios. So next, I will also share you one video, if possible, if I get a time, and I will also play one small video in which we can say that how the work from beginning to the end is happening with the robotics and with the automation techniques. Like let's say from pre-processor to the post-processor, from beginning to the end. Everything is from automation system. No efforts of human being, just robotics arms and doing the 3D printing. So last but not least, about the future trends and the conclusion, I will give an overview about the future trends because we don't know day by day the technologies are implementing, and these technologies definitely can implement for the additive manufacturing. And then I'll finalize with the conclusion about my presentation. So let's begin. As you can see it in the introduction, as I told you, since from 3 days you have been learned many things about the additive manufacturing. Just I will revise one more time with you what is additive manufacturing and where the additive manufacturing is useful, and how we can use this for the different applications, what kind of materials that you can use it for the additive manufacturing. Let's revise all those points. Let's start. What is additive manufacturing, which is one of the most common and basic questions, before you're going to start any topic related to the your presentation, like why I'm doing this presentation and why it is important and why it is required. So let's talk. Let's call this question. What is additive manufacturing? So simple words, as I can say, additive manufacturing builds object layer by layer from a 3D digital design, converting virtual models into the real components. It's also you can say this, it is reducing the human efforts and giving the full product using this technique, manufacturing technique, additive manufacturing technique, and by layer implementation. So these are the keywords that you can say that you can implement in the additive manufacturing. Let's move to the next point. Okay, when I said additive manufacturing, and when we are doing the additive manufacturing, the simple question, how we can do this additive manufacturing? Am I right? So this simple question, we can, if I ask someone, so what are the main core technologies that you can implement a product? Like first, the most common product, as I can say here, is includes fuse filament fabrication system. Actually, the triple F is the most common system that is using to get in a product, a complete product. I can say. So on the other hand, we also have some more technologies that you can nowadays we are using it. Stereolithography (SLA) and selective laser sintering (SLS), and the direct energy depositions. These are the technologies that using to implement a product using the for the using the technique called AM. So basically, fuse filaments fabrication has been implemented for polymer type of materials, and because now, if I split this technology, if I split the additive manufacturing based on the material, I'm sure you have learned from this about this, because nowadays we are also printing we have also metal printing, polymer printing. So these are the examples. So different types of example, different types of technology that can adopt to print a product. Let's move forward. Next point about what is design freedom. Yes, this is very important. Simply we cannot print anything, right? Until and unless we doesn't know what we are going to print. So the design is freedom is very important, and enables the creation of complex geometries, exactly, allows rapid prototype and customizations without mold or dies, because mold process, dies process is a different that technology is like you can say the energy, we are wasting a lot of energy in this doing this. So when additive manufacturing came, yes, that you can say the cost efficient energy saving methods. Let's move on. Significantly reducing the waste and enabling agile manufacturing cycles. exactly. So which means that without wasting a material and without wasting an energy and without wasting a time, and we can create a geometry, complex geometry, and we can print it. We have to design it, then we have to print, then we can get that print. So let's move to the next point, current applications. This I'm just giving the overview of the current applications because I will go in detail in the next slide. So like used across the aerospace and healthcare system, automation system, and you can say also a consumer goods. So also the aerospace bracket showcasing its versatility means additive manufacturing applications is basically everywhere. It's basically everywhere, from household to technology system. So there is a lot of applications that is there for additive manufacturing, and also it is implemented, and also it is also there in the Medicare healthcare system, which is a good contribution, as I can say, and especially aerospace like NASA ISS automation. Recently, they have launched ISS automation system, where they are use the 3D printing, like 3D printed object in a space. So in aerospace systems. Let's move on. There's a lot of things that we can add it here. So now let's move to the emergence of automation in manufacturing. Like as we all know very well, now we are in the industry 4.0. So think about what happened in the industry 1.0. So basically in the industry 1.0, we have a steam power systems, and we begin the 3D printing from the steam power system to the smart factories with the IoT, AI, cyber physical systems. We are implementing industry 4.0. If we don't know about in 5, we also know some of the points we have put it in the 5.0, what we can implement in the additive manufacturing system. But till now, what exactly existed in industry 4.0 is IoT based system, AI based system, and cyber physical systems that can build and a product using an additive manufacturing system and additive manufacturing. Let's move on. uh, I hope, Dr. I'm not going fast. I think I hope I'm not going fast, Dr. Janardhan. If just tell me, okay, if I'm going very fast. Okay, now let's move on to the core objectives. Are you there, Dr. Janardhan? Dr. Janardhan?
Tell me, sir.
Yeah, yeah. Okay, okay. Yeah, just I
Hello.
wanted to
Yes.
confirm. Yeah, I'm in the full screen, so I don't know.
Yes, sir. Yes.
Yeah, yeah. Okay, fine.
Yes, the
So
screen
let's
is
move.
visible, sir. Screen is
Yeah,
visible, sir.
fine, 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 Dr. Janardhan. Just I just wanted to know whether I am going, whether there or not. Let's move on now. Core
No, it is visible,
objectives.
sir. Yes.
Yes, yes, yes. Okay, thank you. Core objectives. Automation aims to increase the efficiency, reduce the cost, and enhance the quality, improve the workplace safety, and support the market responsiveness. So basically, if let's say if I'm implementing automation system in additive manufacturing, what I will get it. So maybe instead of I am printing 3 specimen, instead of that I can print 5 to 10 specimen. I can save my time, and I can give the product number of products. So also when there's a time saving, definitely there's a cost saving also. We can also say that cost saving, and also we can enhance the quality, because once we did the setup, and like robotics arms are example, and I have settled, I gave input to the robotics arm. This is the procedure and this is the outcome I have to get it. So what it will happen? Definitely he will follow the same code, or you can say Python code, whatever the code implemented, I implemented to do this process. He will use that code, and repeatedly he will do the same work. And instead of 1 product, we can get 3 product instead of 3, 5. It means we can increase our productivity. And safety also important, because sometimes it is very hard materials, and maybe it will be problem, sometime, something happened. So this safety also there if you're using the automation system. Support market means we can also use for the market support, such as, for example, like delivering system and advertising system, like this. Let's move forward. Smart manufacturing. Simply, we can say manufacturing means there is a procedure, follow up the procedure, do the step-by-step method, and get the product. Am I right? So let's say smart manufacturing means what? So it involves the integration of real-time data and also a robotics use, and also I can say the AI for adaptive and the modular production system. Uh, I'm getting a disturbance. There is some sound is appearing. Okay. Uh, Dr. Venkatesh Rao, can just switch off your, just close your mic because I'm getting a disturbance. Venkatesh Rao H. Yeah, there's a disturbance from there. Yeah,
Yes, sir, it
fine.
has been done, sir.
Yeah, fine. Thank you. Okay, let's move on. Okay, smart manufacturing. I'm talking about the smart manufacturing. As I can say, the smart manufacturing involves the real-time data. It involves the robotic system. It involves the AI for adaptive and the modular production system. AI is very important nowadays. Everywhere AI is there. So we have can say AI is also in automation system for additive manufacturing. Let's move on. Impact on additive manufacturing. Like what will get what is the impact? If I'm doing this process. So additive manufacturing benefits from digitalization, enabling the digitalized on demand production, and fostering flexible manufacturing models. Means we can get an these are the impact that we can get it enablings. So industry revolution progress. I just want to revise here at this point where we are in right now. So basically, it starts from industry 1.0, I can say, where the mechanization, water and steam power system used to generate end product. This was the initial steps. And there's a lot of efforts. With that lot of efforts, a lot of energy, and lot of building a big space, utilizing the big space areas, and many more things. That time it was like in that time, in 18th were used to build any product. So now let's move to the industry 2.0. After that, what happened in that industry 2.0? Mass production, electric power system appeared, and they use the electric power system, and also they use the assembly line, because assembly line means there is a process system from one by one. Start from material collection, then material joining, then melting, then filament preparing, something like this. There's a assembly line. There is from beginning to the end has been used to get any product. So once the industry 3.0 came, then computers has been utilized to initiate the process, and to give the command for the product. And that you can say what added in the industry 3.0 is computers and automated system, and we get the more productions, and also use the electronics devices that to get the product. So these industry 1.0, industry 2.0, and industry 3.0 has a we just trying to push the mass production system. So now when we talk about the industry 4.0, which is right now we are having it. So in that system, cyber physical systems appeared, and IoT based system, networking systems, and artificial intelligence, and has been using. And because of that, we are printing a polymers, we are printing a metals, we are printing a smart materials, we are printing a ceramics. So many more materials we are printing it, and also we are printing a different kinds of complex geometries, simple geometries, linear products, non-linear products, so many more things. So next, think about the future. In the future, what is the main implementation adding in the future is called as human machine interaction. That's basically named as HMI. So human machine interactions is implementing where human is giving the command to machine like robots, and these robots are working and giving the output. So conjugative systems, and then there's a DT, means digital twin system. So these are the feature, already they have there's a lot of research going on these topics, and they also have some sample and prediction models that showing that industry 4.0. And these comes under the mass customized production system, push and pull system, you can say simply. So this is what basically industrial revolution progress from industry 1.0 to industry 5.0. So in there, we can see, you can clearly see the enhancement, you can see the improvement, how it happens. Therefore, nowadays we have a lot of examples, a lot of products that we are using that came from the additive manufacturing system. So let's move on. Because now I just mentioned about the what is additive manufacturing, how where is the additive manufacturing is useful, and how the additive manufacturing automation is there. So what kind of additive manufacturing materials that you're using to print it, right? This is very important, and I believe that you also know about this, but I just wanted to revise at this point what kind of materials are useful. Basically, as I can see, polymers, one of the most common material that used in for the additive manufacturing. This is also called as non-metallic materials are high in additive manufacturing system because it is easy to melt and build a product. So therefore, there's a lot of polymers like PLA, PP, ABS, PET. If you go in details, there's a lot of research paper that has been shown about the polymers used in additive manufacturing system. And next, talk about the metals. Yeah, metals, one of the complex, method that additive manufacturing system are doing it right now, because they have also product in metal products like lightweight materials product that you're using in the aerospace system specifically. And next, the fiber reinforced composites, because fiber reinforced has high strength, lightweight. Because of that, uh, additive manufacturing research is going in this using this material as well. Smart materials for the healthcare, for medicine, smart materials are using too much because it has gives impact on, you can say that using the materials, for example, like shape memory alloys. Specifically, shape memory alloys have been implemented for the bone type design and other equipment. I'll show you in the next slide what kind of medical applications smart materials. And one more materials that's called as a piezoelectric materials. Yeah, piezoelectric is very important. You can know piezoelectric transducer. Basically, that gives the force, and also that generate the energy like voltage. So some product I know has been implemented using the smart materials. So ceramic as well, and ceramic, specifically ceramic for artificial bones, printing the artificial bones. And for there's one more last is bio ink. Bio ink material most probably has been used to identify heartbeat rates, and and some of the other points like cells, body cells, where the bio ink materials are using. The product has been creating using the additive manufacturing system. So let's see the application one more time. I'm revising the application with the pictures. It's to be. I wanted to be clear here at this point. Why the additive manufacturing is important and how the automation comes with the additive manufacturing. So let's revise what are the applications. As I mentioned in the before, aerospace and defense. As you can see the photo of this aerospace and defense, and the space applications, aircraft designing, or rocket designing or helicopter designing, and space shuttles, space systems. There's a many more aerospace and defense systems where the additive manufacturing products are using it. And next is the healthcare. As you can see in the healthcare, basically healthcare using the smart materials product, using the bio-ink products, and also using the ceramic based product to implementing on bones, to checking the heartbeat, to implementing on cells. So in these areas. Then food industry, yes, in the food industry, even though some of the food has been preparing using the additive manufacturing system with a complex geometry structures, you can say it. And the automotive system, like right now we have now, like you can see the best examples, high speed cars are the lightweight cars, are the lightweight, and they are using composites, high strength composites, and these composites are printing through the automotive through the additive manufacturing system. And engine, because the heavy engine is trying to make it low weight engines, so therefore some of the parts of engine with the metal printing, using the metal and adding the additive manufacturing, they are implementing for automotive systems. Let's move on to the architecture and constructions. Basically, whenever there is a design, to build a new design, what will happen? The prototype model is very important. So in that case, what engineers are doing it, they are trying to build the entire structure, prototype structure, to show that what happening in this next, what happening with the design, like how they are building this construction. So that's what designing architecture models using the additive manufacturing are implementing nowadays. Also in the energy system, like let's say electrical engineering equipments, DC motor devices, many more energy system, solar panels, there the additive manufacturing products are useful. And the fashion industries, like dresses, sandals, shoes, many more products are being created through the additive manufacturing system. So that's it for the introduction section, where you learned about what is additive manufacturing, what kind of materials in the additive manufacturing, and what are the applications, how the automations implemented in additive manufacturing. So these are the things we have just overviewed in the introduction. So next, I will move to the integration of automation with additive manufacturing. What is uh, like my presentation aim to add automation system with additive manufacturing. So now I will revise this slide one more time. Now you can see why automation in AM. This is my question. So now let's say, to reduces the manual intervention. Okay, because there's a step, step one, step two, step three. Again, I have to repeat the step one, step two, step three. Again, I have to repeat this. So what I'm basically trying to reduce this manual intervention. Second, faster production. Definitely, if I'm reducing these efforts, what will happen? I'll get more products, as I mentioned in my introduction slide. Instead of producing one slide, I can produce the 3 slide, 5 slide, like this. Improve the accuracy. So initially, maybe I will not get the full accurate model. Maybe there's some error, some human error, or some robotics, digitalization errors. So what are the errors? So what I'm trying? I'm trying to improve this accuracy of productions. Scalability for industry use. Scalability for industry use means there's a proper way, to that you can use for the industry. So now again, I will move on in detail, like how that's what I said, scalability. So there is some challenge, scalability challenges, like overcomes limitation of traditional additive manufacturing in scaling beyond the prototype by reducing the manual handling and labor intensive post processing. So because what happening basically, there is a step, you have to, what you have to do, you have to initiate the print. Then to initiate the print, you have to choose the process from the screen, one by one screen. And after that, the printing will appear, the printing will be start. And once the printing end, you have to take it out the specimen, keep it for the dry. A lot of these are the procedures. Basically, we are trying post processing system, reducing the post processing work. So now precision and reproducibility. Precision means accuracy. I'm trying to increase the accuracy. I wanted to maintain the same temperature, same amount of material composition, and same amount of like same temperature, same flow, the printing flow, everything. Like automated system ensure the consistent product quality by minimizing variability in layer adhesion, temperature, and material flow. What will happen? Let's say an example. If I set for printing for the 25 minutes, so in the 25 minutes, what will happen? Let's say there is some height of my product. So initially, with the melted temperature, initially the printing has been appeared. When it's go to the final phase, the initial phase temperature is different from the final phase temperature. This is one of the main problem I can say in the 3D printing applications. So because of that, what will happen? The mechanical properties will change. So what aim to an automated system to keep the temperature with the same range, and trying to we are trying does not change the properties, in the material properties or the material flows. This is what trying to do in this automation system. So next, go to the reduces the cost and labors instead, because robotics, if I implemented robotic system, what robotics will do? Robotics will follow my procedure. The same procedure will follow, and he will repeat the things. Like, because simply what is this? First time what you are doing it, you have to do it the next time, other times. So basically, I can say this is the passive work, not the active work. Because you are not thinking to do something very new every time. What you are doing, you are just creating the product, same product. So therefore the same procedure should be there. So in that case, what I can do, I can just set an automation system to do the same procedure and give me the product. And like enables the light out manufacturing through the lower labor dependency, and leading to reduce the operation cost and improve the machine utilization. So I'm just trying to enhance the machine utilization to get more products. Okay, so let's move on. Facilitates smart factory integration. So now, where it is, like automation in additive manufacturing, where it is there in the Industry 4.0. So now we can say yes, this is definitely this aligned with the Industry 4.0. So allowing for the data-driven network production with the real-time monitoring and adaptive control. Because if there is an automation system, it is also easy to observe what happening in the real-time situation. So like whether the product is properly printing or not, or there is something happen in between the machine or in between some with the product. So this is easy to access through the automation system. So now let's add one more type of system that's called a cyber physical system. CPS, basically it is called as a CPS, cyber physical system. And where you can see defining the cyber physical system means CPS integrates computational algorithms, because without the algorithm you cannot give the commands to the robots or to the any kind of machines that to follow this method. So that's what, cyber physical system is very important. Sometimes, nowadays you can see the research, what happening, they are building the robotic robots, and sometimes robots are behaving very bad, If there is no proper command or no proper algorithm, it will not properly, step to what you want to do it. Sometimes it will, the command will be, command will not work, it will behave differently. So that's important. So with the physical process for autonomous control, because monitoring or adoption in manufacturing. Anyways, so this is just you are stepping out to the like what happening and how it is happening, properly happening or not. So now say IoT, Internet of Things enabled AM infrastructures, because it's very important. IoT is nowadays IoT Industry 4.0 is too much contribution of IoT, because the 3D printers with the IoT sensors enables real-time monitoring and the predictive maintenance and the remote operation through the cloud platform, because there's a lot of cloud data, and that cloud data IoT system and enabling IoT system, it is good for following the steps. What are the steps is there for printing the material? Okay. Data-driven manufacturing, yes, because we have a different kind of data, like what are the parameters? Let's say continuous feedback loops, optimize printing parameters like temperature. We have to follow the different kind of temperature range. We have to find out different type of speeds, different layer bonding for improve the reliability and efficiency. Let's say an example. Let's have a good example. Like say uh, for printing the metal, I doesn't want the same temperature what I want for the non-metal materials like polymers. So in this case, my temperature is different for polymers, my temperature is different for metals, my temperature is different for smart materials, for ceramic, for bioink. So this is what as I can say, the temperature variation. Let's say if I am using the polymer, in that polymer also, if I change the temperature, different range of temperature, maybe my product have the mechanical property, the mechanical and chemical properties will change. So I wanted to know that which temperature range is good for my product. So that's why in automation, it is also easy to set the temperature range for the for the product. And the speed, instead of one specimen I'm getting with the 25 minutes to 30 minutes, whether if I print that specimen using the 5 minutes to 10 minutes, so what will be the output? What will be the impact? That's a important question, right? Because I believe that 10 minutes printing 10 minutes of product and printing 30 minutes product has some difference. Definitely difference. Even the layer bonding, layer horizontal layers, vertical layer, inclined layer bonding, this also will vary the properties, mechanical properties. So this is also very important. So next, move on to the role of smart factories, because when the automation word came, the smart factories should be there. Because my efforts is what? I'm just reducing the human efforts. I'm just trying to reduce the human efforts. So this is called automation system. So CPS, like what we have said, cyber physical systems, transform the additive manufacturing into a self-organizing units within the smart factories and coordinating with the robotics, logistics, and ERP systems for seamless productions, which means that humans does not doing anything. What are the whatever the product we are getting it, we are getting using dependency with the robotics, for the logistics, with the ERP systems, because everything is running doing by this. So just we are getting the production, even though they will the robotic system, it can say, I can say they do the packing system also. To packing system, the complete product is there and they have to be pack in the box. They will do the robotic system will do it in the automation system. So now AI driven optimization in additive manufacturing. Like I believe that in additive manufacturing, optimization is very important, because when the temperature change, the product quality will change. When the speed change, the product quality will change. When the layer bonding layer change, the product quality will change. So how to recognize which is the best one, which is not the best one? So because if say these combinations are best for the polymers, it doesn't mean that the same combination is good for the metals. So every time, different scenarios. That's what, data-driven system is what. There's a lot of data implementation. Even though when I did the research in additive manufacturing with my students, I told to my student, does not believe with these parameters and with these steps. Try to optimize this and find out which is the best for your product. So that's what we have included the design of experiments for our product. So to optimize and to drive what happening with our how we are getting the good quality our product. So now let's say now at this point, AI driven optimization in additive manufacturing means what? Sensor data collection. So printers gathers temperature, speed, and material flow data. So these are the center data collections. So these data will give the variation in results. So real-time analysis, yes, it is very important, because sometimes everything is properly, the machine is properly working, but the shape what I want in their shape, there is some gaps are appearing, some thickness is changing, the thickness is changing, or something happening, layers are not properly occurring. So that's what the real-time analysis is important. So for that is AI monitors for deviation and predict the print quality issues in the real time. So I want to make sure that my product has been built with a good quality and with a good design, with no damage. So this is what I can analyze through the real-time analysis. So automated adjustments. So like a system will do the automatic adjustments. Sometimes if it's not happening, the layers has if I want to make an horizontal layers, I just want horizontal layers every time. So the printer is moving horizontally. So in such cases, system instantly self-correct the parameters like a layer addition instantly. So it means that an automated adjustment means what? It will correct it, and it will, wherever the gap is there somewhere, he'll try to recover that gaps. So continuous learning means nowadays we have a artificial intelligence system. The artificial intelligence is a very big area. In there's a deep learning, there is a machine learning, a lot of parametric optimization, predictions, many more things is there. So I may improve my product at every time. Whenever I'm doing the next printing, maybe my next printed product is better than the first printed product. So this is called continuous learning. I'm not saying that I did the best at this time. No, maybe in the next time better than this. So machine learning continuously improves the accuracy with the each print cycle. So if I'm implementing the AI system, specifically machine learning system or design of experience system or fuzzy logic or logic design, many more things, if I implemented on my product, definitely I can enhance my product. So workflow integration, like seamless link to FRP robotics and quality control system, because I wanted to make sure that my product has a good quality. I doesn't I like I if I'm like it is a PP or PLA product. If I wanted to sustain this product in this temperature, means definitely should sustain at this temperature. If it's not sustaining on that temperature, means it means my quality of product is not good. Anyways, let's move on. Three. Dr. Janardhan, how much time I use right now?
Around 30, 20 minutes, sir. Around 20 minutes.
So I have left only 20 minutes, sir. Oh, I need to go
sir,
fast.
Around, sorry to say this, sir. Around 36 minutes, sir.
Yeah, around 36 minutes, I think. Yes. Okay,
Yes,
let's move on. Next
Yes.
step, next is the technological infrastructure. The third point where I want to talk about technological infrastructure means what? Uh, like I have different technologies. I wanted to build in the additive manufacturing. So I have a architecture. How the, like, as you can see this figure. Can you imagine there's a like you can see there's a one figure has a computer screen, one figure has a cloud system, one figure has a radar system, one figure has a satellite system, one figure has some other like multiple object system. So now I wanted to combine these systems in a one cycle to get a product. Additive manufacturing automation and additive manufacturing product. So what will happen? As you can see here in the next point, yes. See how it is interrelated to each other. Computer is related to radar system is related to satellite related to networking layer, networking related to interface layer. So these are the IoT architecture. I can say these are the IoT Internet of Things architecture, where these points are very, very important for automated additive manufacturing, not for the additive manufacturing. I'm talking about the automated additive manufacturing, in where human does not have any efforts. Everything is done by the robotics or any object. So like that's how sensible layer. So proper sensible layer happening. Embedded sensor gather the data from printers to and materials from printers and materials during the AM process. So means embedded sensor means sensor is very important to gather the data, to print a proper way using the material. So next, you can go the networking layer. Sensible layer about that networking means you have there is a network, without the internet or without the IoT system or without any other wireless system, you cannot make sure that there's a proper connection between the machines, between the screen, between the internet. So networking layer is very important. Technologies like 5G, IoT, and wireless system ensure the reliable machine-to-machine communication. There's a proper communication. Like my system is giving a right command for the right printing. If there is in between there is a miscommunication, what will happen? Yes, definitely you will not get the result. So service layer. So cloud platform handle the data analytics, AI-driven control, and the storage of information. Yes, because if there is no storage of information, what I'm going to do? I have to give a command. I'm created a program, Python program. Yes, this is my program, and I want this print. So once I give the command to that, there's a data-driven control. Because it's controlled, everything is controlled, right? And then based with the control, you are getting the right product. If there's not control, you will not get the right product. So last, but in the here interface layer, dashboard provide a remote monitoring capabilities linking the operators with the AM machines. So in the dashboard, I wanted to command, yes, print, continue, select the material polymer. Yes, this is the command what I'm giving on the screen to get the print. Okay, now what are the hardware and what are the software that is important to do the automation additive manufacturing system? Robotics hardware, arms, conveyors, automate, part handling, and logistics is very important. The arms is giving arms is taking the product from the machine, keeping for dry, and then next preparing for finalizing, preparing for finalization. So these are done by the arms. All this done by the arms. That's called the robotic system. So smart monitoring system and AI control, because smart monitoring, I am observing how much the temperature is set and whether the temperature is same or not. 23.8 is example, degrees Celsius. Yeah, temperature is there in the same control. Now you can see the controllers, whether the process in controlled condition or uncontrolled condition. So I need to observe whether the monitor, whether it is the control condition or not. So for that, sensors continuously track the process data. If I implemented the sensor, it will track the process data, and AI predicts the failures early because I have my machine learning process. I already gave the machine learning what is the what is the failure system. I have already trained for the failure system. Now I can test it here and I can know whether it is properly working or not. And optimization print in real time. So I can say my optimization, my printer in the real time situations. So now go for the CAD/CAM software. Why the CAD/CAM we are using it? I am not limited here for the CAD/CAM. I can also add the other softwares, the Star CCM, ANSYS, and Abacus. There's many more softwares. You can design any object. That you can design any object for printing. So integrates the design to product workflow from the AM machine. So like let's say I have designed using the CAD/CAM software, and later on what I will do, I will just take it out for printing. Even though this is we have done in our Prince Sultan University with one of my colleague. So we have did the design in Abacus. The design we use the biomedical design to print it. So later on we printed. So this is we already did it in our lab. So last but not least here, MES ERP integration system where you can connect the cells to one another, connect the cells to one another to enterprise planning and resource system. So everything, cells, from cells properly appearing and how it is moving next to the MES to ERP. You can check it with the, you can add in the software system. So now some challenges, I wanted to add it here, like challenges in a quality control and standardization, because definitely if you are doing something, definitely you have advantage as well as you have disadvantage. So we cannot say I'm the perfect or the 100% perfect. No one can say in the world. There is some challenges, some difficulties, some limitations. So it is important to put it here. What are the challenges is there in the quality control? Dimensionless accuracy and surface finish, because you can see the product of, if you are doing it in your lab, you can see the surface finishing is not accurate if you are using the other manufacturing system. So sometimes, AM, the layer what I'm using, the layer by layer system, that layer by layer system will appear in our final product. The layers will appear in the final product. I have example, we recently did the dog bone samples for the PLA and PP materials, and we saw it. The samples has layers, but the finishing is not clear. So researchers are trying to do this. They're working on this to implement, surface finishing proper, way. AM parts frequently show deviations in the tolerance and the surface finish. This you can also see if you are having the lab and doing the research. You are very, very sure about that happening with your product. Porosity detection, because hidden voids within AM parts can compromise strength, and necessitating the advanced imaging like techniques for detection. Sometimes porosity, not properly assigned. There is some weakness in some area of the product, and in some area is very high good strength. So this is also one drawback, as you can see. In process verification, because continuous monitoring during the AM process is crucial but difficult to standardize. I don't say that it is the proper standards I'm following it. Like I'm preparing for tensile test using UTM machine. I have a standards, ASTM standard. With the ASTM standard, I prepare the sample and do the test. So there is no standardization here because we doesn't know about the what we are doing. Basically, in the AM, we are doing still the AM is on research mode. I can say still is on research mode. Day by day, enhancing that product. Every time we are enhancing the product. Someone says 10 minutes is a good time. Another guy says 15 minutes was a good time. And then next recent guy says no, 20 minutes is a good time. So these are the happening. There's no standardization. Which standard that can say the product has a good quality product within this time. So not only time, temperature, speed, many more parameters. Regulatory compliance, yes, as I told you, does not have any regulatory compliance. Existing standards from bodies like FDA, like ISO, are currently lagging behind the rapid advancement in the AM technology. It doesn't have a proper, standards that we can say following this standard, the product came and that product is a safe product and we can use it. It doesn't have this. So now let's move on strategic value and impact if I'm doing it. So mass communication via automation. So I have a product, I have a lot of product, So there's a mass production, mass customization, like you say. Digital inventory, like parts stored as CAD files, produced on demand, like whatever I design. Yes. So on-demand manufacturing, like someone has asking me, I'm getting a disturbance. Yeah. On-demand manufacturing, someone need a product and he's looking for it. So what the best method is additive manufacturing, eliminating the warehouses, enabling just-in-time production. So patient-specific healthcare, custom implants, orthoses, and prosthetics manufactured per patients. So these are we have also a prosthetic lab in our university where we are trying to product the artificial legs, artificial hands. So now consumer personalization, like footwear, e-wear, and devices tailored for the end users. A scalable automation, like robotics, enable high throughput without losing customization. So now sustainability and material efficiency, that's important. Like reduces the waste, because if you are using a simple additive manufacturing system, maybe you will get a more waste materials, So layer by layer deposition in automated manufacturing minimizes the scrap compared to the traditional subtractive method. Like traditional method, manufacturing method and automation manufacturing method, you will get, you will try, you can say that reducing the waste of material. So recycled feedstocks, like automated additive manufacturing system effectively utilize the reprocessed polymer and metals. So again, use it and make a product. Energy efficiency, process monitoring, optimize the cycle to lower power consumptions because it doesn't need to require human efforts, like energy, high voltage or say high and other effects, energy effects. Reduces the life cycle impact. Digital workflows lead to decrease the transport, storage, and carbon footprint. This also can reduce. Enhance the circular economy. Closed loop recycling strategies are employed to improve the sustainability goals. Like you are using the same procedure, so closed loop we can call as it. Okay, here case studies. I will just talk about the case study, and if possible, if I have a time, I'll also show the one video. I will not. I will. If I take the video, it will take a long time. I will just show you the final video. What happening? Let's talk about a case study. One simple example. Before that, I will just do this one. So AI-driven custom production. Okay, where there is a one product robotics arm. That arms, what they are doing, they are just printing the product and preparing for delivery. So like AI-based optimization, like there's algorithms automatically adjust the production parameters like temperature, speed, and pressure. Okay, where the workflow automation, AI significantly reduces the manual scheduling and inventory management, achieving a 30% of reduction. Very good it is. As per the traditional method and the automation AI method is reducing the 30% of reduction. So mass customization, AI enables the instant adaptation of customer specific design for production. So if I use the AI, so real-time quality control and scalability. So machine learning ensures the quality with the minimal human oversights. and the system can scale from prototype to industrial scale production. That you can use it here. So like you can see here, Industry 4.0 and smart materials in AM. As you can see, there's a one guy who doesn't have the one leg. So in that case, like artificial, leg are built it already is built at such a then it's where we can use it. This product is manufactured using the technology AM in where now the smart materials in healthcare, 4D printing and medicine 4.0 and personalization. So smart materials in healthcare means with the help of smart materials like shape memory alloys or piezoelectric materials, piezoelectric material that used to implement the medical devices like stents and light representative smart gels are being developed for application like control contraction. 4D printing, because as we all know the 3D printing, right? That's the one more 4D printing. This technology utilizes the materials that can adapt their form and functions in response to the external stimulate such as heat, stress, or moistures. So now Medicine 4.0 and personalization, where you can see the smart additive manufacturing facilitates mass personalization of medical devices, leading to patients specific prosthetics and wearables. And programmable materials are driving regenerative therapies and bioprintings. This is the one of the good contribution through the additive manufacturing system. So now case study low cost robotics AM cells, where you can see it is giving you the whole process from pre-process to the post-processor. Means he set the robotics arm set the printing process, then he took the printer, he just opened the printer, he took the sample and put it on the box to deliver. So these kind of things has been done through the object like automated part removal, boxing and print again restart. It follows the same procedure. Hardware, like they use the hardware, the microbitic 280 two-finger gripper and enclose the triple F printer. So control means there's a control system using the Python and record it, and there's a loop logic revising the same procedure. So routine, open the door, grip and twist, then bin, then start and continue. So it means he's revising. He's doing the whole process. Outcomes: 3-cycle run succeeded, test printed, speed of 25 to 5 minutes. In 5 minutes, he just prepared the 3 samples. So this is the video in where you can see the product, how they are built it. I will just give you this video. Just you can see the last 3 minutes of the video. How much time do I have, Dr. Janardhan?
Sir, you are having, sir. You can continue, sir. No problem.
Okay, thank you so much, doctor.
Thank you, sir.
Yes,
Thank you,
yes. I will show you this small video in where you can see. Can you see this video, Dr. Janardhan?
Yes, sir. It is visible, sir. Yes, sir.
Okay, fine. Thank you.
Okay, fine, sir.
Yes.
Thank you. Audio not audible, sir. Audio, please switch on the audio. Audio.
There's no sound?
Yes, sir. In video, there is no sound, sir.
There's no. Oh, how can I, add this sound in the? Do you have an idea about this? Just I'm trying to.
Otherwise, you just play, sir. Otherwise, you'll send the link. I will play. Otherwise, sir.
Yeah, if I send you the link, will play?
Yes, sir.
Okay, fine. I think I can also try to this one more time.
Sir, once you reshare your screen.
Yeah, it is there. Here it is there. Okay. Now you can just check.
Tiny robot arm.
Yes, sir. Yes.
It's called
Done.
the
Okay.
Cobot 280. I'm curious to see if it's capable and strong enough to help me automate my 3D printing. Let's open it up and check it out.
So I will just take it out here.
This robot arm is modular, which allows you to connect different items with Legos. If you've never programmed a robot arm, that's okay. This is my first time, so we can learn together. The programming language for this is Python, which I haven't used in a long time, and even then I didn't really know it that well. But luckily it comes with another program called MyBlockly with easy to use drag and drop features, which allows you to program the robot arm very easily. 3D printing has come so far over the last 10 years. I've been 3D printing since 2017, and it has just become so easy and so automatic. You can print from your computer, from the printer, or from your phone, even in a different country. There's one thing you can't do today that we're trying to solve with this arm, and that is removing a part off of a print bed. I've seen videos where they've automated the process by knocking the printed part off with the head of the printer, just like this. The problem with that is, what if you want to print with ABS, which has chemicals that you do not want to be breathing in, and you need it in an enclosure with a filter, or maybe you need another part that needs a heated chamber so it can print better. Those type of materials require an enclosure, which comes with a door, and it can't just knock those parts off without hitting that door. I'm hoping that this robot arm can open that door and grab that part and put it in a box for you and start the next print. Before programming anything, we need to make sure that the arm is in a spot where it can reach the printed part, it can put it in a box, it can just do everything that I need. So I'm going to move it around a bit and see if I can find that sweet spot where it needs to be without getting in the way. When I turned on the robot arm, the servos were locked, which means I couldn't do this. So before I could do anything, I needed to unlock them by using this snip of code to unlock those servos. So like I said, my plan for this arm is to grab the print off the bed, which means it needs to open the door, grab the print, put it in a box, close the door, and start the next print. I'll be testing this arm with chess pieces. They're light, and I think it's something that it could pick up and easily put in a box. Now that I have the robot arm in a good spot, I'm going to anchor it down. That way, as I'm testing it, it's not going to get moved and have to start over with all the programming. Something that makes this arm so easy to code using MyBlockly is I can situate the arm where I want it to be, record those coordinates or those angles, and then have it go to that spot. We have set the angles for our first position. Let's go ahead and see how it works. Okay, that worked. Let's move on to the first step where we're opening up that door. So I've run into a problem. This door has magnets on it because without the magnets, when it's printing, the door will start to slowly open. I was worried at first that I'd have to stop and not use this printer. Then I had the thought, let's remove those magnets and see if we could open that door. Okay, I've got the magnets off. I've put a little more programming in there. Let's see if it will open the door and get ready for the next step. That is so cool for some reason. I opened a door with a robot arm. Whoop-de-doo. Now it's time to find the next
I think I
position
will
and
just
test
move to
those
the
angles.
last point, some of the points.
Your workflow is important to us. Please wait indefinitely.
With Monday.com's intuitive work management platform,
Now it is giving the
And
command.
it works. Now let's talk about how you start another print. Now the great thing about this printer is once a print is finished, if you want to repeat that same print, it just takes one button. You just click continue. Okay, let's try this step where it starts the next print and then holds that door shut. Again, we don't have those magnets there. Awesome, that worked. We have all three pieces working. It starts a print, it waits for it to finish, it grabs it off the bed, but I don't have it where it repeats the process 3 times and putting it in a different box. I'll go ahead and get that programmed and then explain what I did. All right, let's talk about this code. So this first line, when it gets to this section, and we get into this, we can do 3 prints, put them in each box, and then finish. You'll notice we set the variable box to 1. We set it to 1, so when it gets to this section, if the box is 1, it will move the part into that first box. After it drops that, we will change the box by 1, so it'll go up to 2. So when this whole thing repeats, it will then take the part to the second box, and then as it repeats for the third time, it'll take the part to the third box. We just have 3 boxes, but imagine doing this with 10 boxes, 20 boxes. The possibilities are endless. And here's the last bit of code where it will sleep until it repeats that last step. Okay, we have finished the code. Let's see this thing in action, performing each of the steps where it's starting the print, taking the chess piece, putting it in the box, and starting the next one, doing that 3 times. Before I click run, if you want to buy one of these robot arms, I'll put a link down below. If you use that link, you'll get 5% off thanks to our sponsor, Elephant Robotics. Also, don't forget to subscribe. We're almost at our next subscribe goal, and it really helps us out. That was amazing, and it answers the question from the beginning of this video, is it possible to...
So this was the example as you saw it. So let's continue my presentation. Okay. Okay. As you can, yes, Dr. Janardhan, can I continue now? Yes. Dr. Janardhan, can you hear me? Hello?
Yes, sir. You can
Yes,
continue.
okay. I'll continue now. As you saw the video, it was a very good video, that shows, this is the example what I have shown in the video. This is the example in which you can see the robotics arm like automation system, it begins from the from this from the initial stage to the final stage, and it printed 3 chess some specimens that you can see through this video. So this is the called as basically this is a case study. I have shown the best example. This is one example I can say where you can say called as a automation in additive manufacturing. But this is not limited. This automation is to just to get a product and put it on a box. But this automation system also can be utilized for the production system. To set the proper temperature, to set the proper speed. There's another view also. That you can call as automation in additive manufacturing. This is one of the example case study that I've shown you. So now let's move to the last part of my today's presentation because there's a one word that can I say, no end of research. So research is always, there's a life of research is always increasing. So future trends and conclusion. So let's see what will be the future, So the future of automated additive manufacturing that can be, autonomous factories, decentralized additive manufacturing hub with a minimum human oversights. Means what? Basically, implementing robotic system and reducing the human efforts. So I wanted to say that basically what happening? We are reducing the jobs. Anyways, so now digital twins. I think before my presentation, someone has presented about the. I think this is one of the point twin system, right? So that's one about that. They talk about that. So virtual models for predicting and optimizing production cycles. So this is called digital twins. AI-driven ecosystems. So nowadays, integrating AI for the additive manufacturing has a mass production. So integrating AI, managing design, production, and logistics. So therefore, we have a lot of we can get a lot of product. Now, sustainable design, like closed loops recycling in line with the climate targets. So based on the climate, we can create a closed loop systems that can properly operating and repeating the same procedure. So industry X vision. So what I can call here industry X vision is what? Simply I can say industry 5.0. So next generation manufacturing emphasizing the resilience, adaptability, and the scale. So industry X vision is X. Why I put it X here? Maybe 5, 6, 7, 8. So always there is an implement. So let's move on to the next vision. Like let's say industry 5.0. So then I don't know in the 6.0 what is there in the next 6.0. So in the 5.0, what is the main implementation in the industry 5.0 is a human machine interaction. Okay, so human machine interaction means human is giving the command, a machine is properly operating, and it's not operating only for the product. From like everything is done by packaging, finalizing product, initiating product, everything is done by the machines. I know in the industry 4.0 also there's a machine use of machine where you can print the product, but here completely humanized machine, you can say. It's giving everything to you. Just you are sitting and you are giving the command and everything is you are getting it very nicely. So let's like you can see here, this is the one example. You can say a 3-level model. This is the 3-level model where HMI 3-level HMI model for additive manufacturing 5.0, where you can have a ecology, economic, and product design. This is a 3-level process. In there, what happening? People orientation, robotness, and sustainability. Because nowadays our main focus is what? In the sustainable goals. You can see the sustainable goals. So in the goal, we have to. This is very important. So now, physical, human, and information system on the other side, because information system is these are the interrelated to each other. Human information interaction, human physical interaction, and physical information interaction. These three are the interactions where very useful for Industry 5.0. This diagram shows a 3-level HMI additive manufacturing for the Industry 5.0. So where you can see what are the important key object that is interrelated to each other for the Industry 5.0. So another example you can see that I can say a development process. So industry like 3-level process, then development process. In the development process, what is happening? Day by day, you have a development using the data optimization techniques like design of experiment, machine learning, deep learning, fuzzy logic, many more applications. So every time you have a development in the defining the temperature, defining the speed, defining the material, defining the layer, everything. So what is key factors and how it is important, like information systems and physical system. These are the two systems is very important, that is interrelated for Industry 5.0. Then user, design, and engineer. These three factors that can give the for giving the command. Then maintenance manufacturing and conceptual design and detailed design, because everything, first what you will do, first start with the conceptual design, then go to detailed design, then manufacture. Am I right? So this is the process. So based on this, you will get the product. So in the manufacturing, maintenance manufacturing, data transformation is very important, because if you have proper data, then you can optimize or get a right product. Then conceptual design, detailed design occurs also in the data transformation, because let's say we have a huge amount of data, huge amount of variables, huge amount of parameters. How to optimize these parameters, that is very important. So you will get in Industry 5.0, it will be very easy for you to optimize the data. So now, I think now I'm in the conclusion. I hope the points what I want to deliver, I delivered it properly. So now let's talk about the strategic implications, with the conclusions. So scalable production, like automation, enables AM to transition from prototype to mass production. Okay, not a single production. So now sustainability focus, because sustainability focus and sustainability goals is important for us. So automated recycling and efficiency support climate goals. Support the climate goals. Now the quality assurance, this is always engineers, scientists, researchers, they always focus on the quality assurance. The quality is important. Closed loop monitoring ensures reliability for critical industries. So strategic adoption, firms must invest in CPS, AI, and IoT integration. These three integration to get the, I can say this is what. Customization advantage, like mass personalization drives competitiveness in healthcare and consumer goods. So last but not least, global supply resilience, because automated AM localize the production, right? And reducing the resilience actually on fragile supply chains. So this is a proper implementation. So that's it from my side, and thank you for the listening my presentation. If you have any question related to automation, additive manufacturing system, you are free to ask. I'm done, Dr. Janardhan.
Any student, audience, anybody is having any question, please ask. In audience, if anybody is having any question, please ask. Even if you can post in the chat box as well. Any questions?
If there's no questions, means, Doctor, I think it is very bad or it is very good.
It's very good, sir. You have delivered on the latest technology of both involvement of AI, even related to the industry 5.0. It's good.
Yes.
I have enjoyed your talk, sir. I hope others have also
Yes.
done the same thing.
That's what I am saying. That if there is no question, means either you can say it's very good or it's
No,
very
sir.
bad.
No,
Hello,
it's
sir.
very good, sir. It's very good.
Hello, sir. I have a
Yes. Okay.
question,
Thank
sir.
you. Yes.
Yes,
Yes.
come, sir.
Please.
Please, please, sir. You can ask your question, please.
Okay, sir. Sir, my question is, we are using many additive manufacturing processes like different methods like LBPM, DED, DIW, and all of these things, BHAT processes, all of these things we are using. Sir, can you tell for prediction purposes, what are the recent new softwares have been made? Recent new softwares. That's why you can simulate or predict.
Yes. Very good questions. But it is depend. You are trying what kind, like software for what? Software for design or software for printing?
Suppose, sir, we are using software for one, like wire archive machining.
Okay. So basically, you wanted to say that is there any implemented new softwares, right? To
Yeah.
further design. Actually, as you can see, we have every day, we have the day by day, we are the software is going increasing. But what I learned from my source, because I don't know exactly nowadays which software they are using it, but what we learned, we have a inbuilt software in our machine. Okay, this is for the printing. Okay, inbuilt software. This for the printing. That there you can set the proper define the speed, temperature, anything. And if you're talking about the design process, if you want to get a product, now you can definitely you can use ANSYS, Abacus, and create the 3D model. That 3D model you can convert it into 3D printing machines, like what you said, the example of the same software, and print it. This is what I know, what we did it. And apart from that, is there any latest software? Maybe it is there, maybe it's not there, but the same we are using that what you are using it now. And for the design, we are using ANSYS and Abacus. For the design, we are using ANSYS and Abacus.
Thank you, sir. Thank you, sir.
Okay, thank you, sir.
Thank you, sir. Thank you for that, Abdul, sir. Let us today close the session. So thank you for your time.
Okay. No, that's it.
Yes, sir. Thank you, sir. Thank you.
Okay, fine. Thank you so much.
Thank you, sir.
Participants, all of you leave now.
Okay. Thank you so much, and have a nice. I think you have 2 more days, right, left for the